Hello, this is Mrs. Scarpel with topic 2.12, properties of logarithms. You will notice that they're very similar to some of our products or properties of exponents, and that's because logarithms are inverses of exponential functions. So our three properties that we need to pay attention to, the product property. If you have a logarithm of a product, you can expand it to be the logarithm of a sum. If you have the logarithm of a quotient, that's why we call this the quotient property, you can change it to be the logarithm of a subtraction. And the power property, if you have the logarithm of a value raised to a power, that power can be written in front as n times the value of the logarithm. So these are our three properties that we're going to use. You'll see that we have examples right below. Refer to those examples as you look at 1A and B. I'm not going to do them because they're just so similar to what's in the table above. But I do want to talk to you about C, E, and F. So for C, you'll notice that it isn't just one subtraction, but two subtractions. Anytime you see multiple subtractions in a logarithmic expression, you want to rewrite it by factoring out the -1. I know we don't see it, but it's as if each of these have a -1 in front of them. So I'm going to factor out that -1, and that's going to give me log of 5 plus log of z. Now, if you're wondering what happens to the 10, remember, log base 10 is the common log. And when it's the common log, you don't have to write the base. Now that we have an expression in parentheses, let's work on simplifying that first. So we're going to have log of x minus, because we have an addition, we can change this into a product of 5z. So log of 5z. And now we can take care of the subtraction, and that's going to be log of x. The value that comes in front of the subtraction goes in your numerator, and the 5z, because it follows the subtraction, goes into the denominator. Now the difference between C and E is that E doesn't have more than one subtraction. So if you wanted, you really could just go ahead and write all of this as 2 log base 7 of A. This time I'm including the bases because it's not the common log, and write it as log base 7 of 4 next, and then put the subtraction on the end. That is perfectly acceptable. You're just rewriting it in an equivalent order. And then you can work on, okay, let's work on this addition, actually, before I do that, I need to worry about these constants that are in front of my logs. So this is going to become log base 7 of a squared plus log base 7 of 4 minus log base 7 of b to the power of 5. Remember, when you have a power on this, it could be written in the front. Since it's already in the front, we move it to the power. And then I can write this as one logarithm, log base 7. I would take the a squared and multiply it with the 4. We always write the constant in front of the variable term, so 4a squared. And then that subtraction gives us our denominator of b to the 5th. Excuse me. When you see a problem like f, in order to apply any of these properties, everything has to be in the same log base. So this constant 2, we need to change into a logarithmic expression. And we want its base to match the log base 6 of x. So we're looking at log base 6 of what number is 2? So essentially what you need to think of is 6 to the power of 2 is what? Is 36. Excuse me. And that's going to get added to log base 6 of x. So now that I have my expression written in terms of all logarithmic terms, I can apply that product property to be log base 6 of 36x. For example 2, we're going to be going backwards. Instead of having it in a condensed form, we're going to write it in an expanded form. So I see that I have the quotient that tells me that I'm going to have a subtraction. So log base 3 of x squared minus log base 3 of y. And then I need to apply my power rule. This power of 2 needs to go in front of my log base 3. So 2 in front of a log, I don't see that in A, I don't see that in D. I do see a 2 in front on both of these, but because my y squared doesn't have, or my y here doesn't have a y squared, I don't want to have a 2 that gets distributed with this term. So I can rule out B, which means it must be C, because the 2 is only going to apply to this first term. For example 3, we're going to rewrite it to show that we have a horizontal, a vertical translation, that it shifts vertically. Right now it looks like we have a horizontal dilation because we're multiplying the x inside the parentheses there. But if I apply my product property to that log of 6x, I can write this as log of 6 plus log of x. And they didn't give me a base, so I know this is a common logarithm. And when I look at this, g of x is log x. So I have my g of x expression that I need, and then plus k. What that means is this log 6 is my constant k that I would translate in a positive direction log 6 units. I can put that in my calculator and get a decimal approximation. We also have what's called a change of base property, and this can be used if we have an expression in one base, but we need our result to be in another base. So for example, here we have let f of x equal log base 4 of x, and g of x equal log base 9 of x. Show that f is a vertical dilation of g by finding the value of k, such that f of x equals k times g to the x. So what I'm going to do is I'm going to start with f of x, and I'm going to write that as log base 4 of x, and then I'm going to go into my change of base, and I'm going to write log base x over, I don't know what that base is, log base of something of 4. So the base of my initial logarithm now becomes the value that I'm finding the log for in my denominator. Because I'm looking for g of x, if I look at g of x, I see that I have a base of 9. So I have an expression that involves a variable x, and that log base 9 of x is my g of x. So how can I write this to identify k? Well, it's just a matter of writing it in another form, writing it using a rational expression. So this log base 9 of 4 can be written as 1 over log base 9 of 4. And we're going to take that times log base 9 of x. So that log base 9 of x is g of x. And this expression in front is the value that we'd be multiplying by to make it a vertical dilation. So if we take the time to state the value of k, because it did say finding the value of k. Example 3 did not. I can write that k is 1 over log base 9 of 4. And again, we could find the decimal approximation in our calculator. And the last part of your notes is just reminding you that a log base e is the natural log. So all of those properties we've been using also apply to natural logs. So keep that in mind. I'm not going to do example 5 with you, but I would like you to try it. You can always ask me to check your work. Find the condensed form or determine which of these 4 expressions would be a condensed form of this subtraction of 2 natural logs. So just keep in mind natural log is just log base e. It's just called the natural log, just like log base 10 is just a log. We call that a common log. And the same properties apply here. And this concludes our video on those properties that allow us to rewrite logarithmic expressions to help us with seeing types of transformations that take place, or when we get to solving, could help us with solving logarithmic equations.